Hello student to this massive open online course on advanced analytical techniques, and we are in the last chapter of this advanced analytical technique course, and in this unit we are exploring the gas chromatography, and after that we will explore the HPLC. So we have already discussed about GC, that is gas chromatography. We have discussed its principle, we have discussed its instrumentation, and now we are discussing the components, the various components in an individual manner. So in the previous slides, we have already covered the carrier gas, we have covered the flow meters, we have covered the sample injection port, and in the last slides, we have also discussed about the heart of gas chromatograph, that is called as the column. So we have discussed the column, and now it's time to explore another important component of gas chromatograph, that is called as the detector. In simple words, the importance of detector in any gas chromatograph is as vital as the eyes in the human body. So in simply, detectors may be regarded as the eyes of gas chromatograph. Okay, you can say that the separation occurs in the column, but okay, separation has been done. So now how you came to know that how many components are there, how many different components are separated from the column, and what is the quantity of each component. So it is now the detector comes into play. So detector tells you about the different components, that is, it tells you about the nature, and it tells us about the quantity of different components of your volatilized sample. So here the detector is important with regard to the sensitivity, with regard to the selectivity, with regard to the accuracy and the reproducibility. So these five aspects make the detector most important after column. There are a number of detectors, and each detector has its certain advantages, each detector has its certain limitations, each detector has certain set of compounds which it can analyze, and there are certain set of compounds in which it does not effectively analyze. So we have universal detector that is suitable for most of the organic compounds or any molecule that changes with regard to thermal conductivity. And there are two detectors, that is FID, which is called as the flame ionization detector, flame ionization detector. It is commonly called as FID. Then we have TCD, thermal conductivity detector. And these two detectors are called as universal because they are good for detecting almost all the organic compounds, inorganic compounds, and most of the pesticides also. Similarly, sometimes we have to have selective detection, and for that we have these three type of detectors, that is the electron capture detector, nitrogen phosphorus detector. Similarly, we have FP detector. So these are specific for detection of specific functional groups like halogens, like chloride, bromide. Similarly, for nitrogen, sulfur, and phosphorus, for detection, for example, in the detection of pesticides, these type of detectors comes into play. Similarly, we have certain mass sensitive detector. So that is called as the mass sensitive detectors. It actually gives you about the molecular weight. It gives you an idea about the molecular weight and also the structure. So that are the very versatile detectors. We are going to study these also. Similarly, we have some other type of detectors which we are going to see while we explore the detectors in detail. So let us embark our journey. So before going to the details of FID, that is the flame ionization detector, or the thermal conductivity detector, or the electron capture detector, let us first analyze that what are the essential features which must be there in a detector. So the first and the foremost, that your GC detector must have high sensitivity, that it can detect up to trace level, that is at the ppm level, at ppb level, that is up to 10 raised to the power minus 15 gram. It can detect up to 10 raised to the power minus 15 gram of analyte. Okay, so high sensitivity means that it can, it can go beyond the limits. Similarly, fast resolution, that is you will get sharp peaks, and the band broadening must be minimal, that is it must be as small as possible, that is you have to avoid like this. No, this is not advisable. Okay, similarly good selectivity, that is always always alpha must always be greater than 1. So we will see that in terms of universal detector. Similarly, linearity, this is very important aspect, that is response proportional to concentration. It has high linearity up to the level of at least 10 to the 5 times. So it should increase linearly. The response should increase linearly. The moment as you increase the concentration, the response will increase accordingly. So that linearity must be very high. For example, we are going to see in the coming slides that FID has the highest linearity. Around it goes in for FID, it goes to 10 to the 7 times. You can see such a long, it does not have any haphazards, or it does not change actually. Similarly, reproducibility, it gives consistent result. Whether you go for 5 cycles, you go for 10 cycles, you go for 100 cycles, each time you will get the same result. That is called as the reproducibility. Similarly, the stability and robustness, that is your detector should be stable. It should give, it should not, in any case, it should not react with anything, and it has long operational value. It will be good for doing 100,000 and 10,000 separations. Similarly, it should have low noise. Otherwise, if the noise is too much, the sensitivity will be compromised. You cannot measure the current, because here the current which will be coming, for example, in TCDs, that is very low, sometimes on the order of 10 to the minus 12 ampere. So if the noise is high, you cannot monitor that noise of the analytes. Similarly, temperature tolerance. Temperature tolerance means that it must be compatible up to 400 degrees centigrade. That is sometimes the temperature of the oven. Sometimes we need actually high temperature. So these characteristics must be there. But practically speaking, there is no detector which has all these features. At some point of time, we have to compromise 1 or 2 features. But in any case, we have to look for as much features as possible, of all as much features as we have listed here. Okay. So let us start with the one that is called as a universal detector, which is called as the flame ionization detector, or simply FID. Now you can see the pictorial representation of FID. What happens is that this end is connected to the column, and the effluent comes here, and your hydrogen gas, it is actually disconnected from the hydrogen cylinder, and hydrogen gas mixes with it, and there is certain air, and it actually, a hydrogen flame comes out, and it burns, pyrolyzes your analyte. Pyrolysis of your analyte occurs. Your sample actually gets burned, and in burning, it actually, burning in the hydrogen flame, it actually creates ions. It creates ions and radicals, and that is actually proportional to the carbon content present in the effluent. Effluent means, that is effluent actually contains your sample. So your sample your sample contains certain carbon atoms, and that carbon atoms get pyrolyzed, and their pyrolysis actually is proportional to the detectable signal to the current. So what happens is the ions are produced, and you actually connect it with certain electricity, and you actually have positive electrode and negative electrode, and the ions actually move towards it, and you record it as a signal. So this FID is good for detecting hydrocarbons, alcohols, esters, and fatty acids. But the issue with it is that it is actually a destructive technique. It's a destructive technique, because your sample gets pyrolyzed, it gets combusted. So what happens is, initially your sample elutes from GC, which we have seen, and enters into the flame. That is actually the hydrogen and air mixture. If you see here, air mixes from here and hydrogen mixes from here, and effluent is coming from this side. So it burns, and it produces the radicals and H plus ions, that is the CHO plus and C plus, and these ions are collected on the polarized electrode and generate current, and that current is actually measured and in the form of a signal. So this is actually the main equation on which the FID is based. That is, the ions, the current produced by ions is directly proportional to the number of carbon atoms present in the analyte. So FID is good for detection for almost all organic compounds except certain gases like NO2, like CO2 and water. Okay, it does not give any signal for these small combustible gases. So what are the key features? Why we actually called it universal is depicted in this table. So it has a very high selectivity. You can see 10 to the power minus 13 gram. It can detect such a small quantity, and it can detect almost all the organic compounds. It is not good for inorganic compounds. And the range, you can see the range. You can see the range. That is the most strong aspect. It has such a long linear range. Okay, but it cannot detect simple gases like CO2 or water or NO2, and also certain inorganic compounds. Now the operating temperature, you can see it is 200 to 300 degrees centigrade, not so high. Okay, not so high. Now here you can surely use nitrogen, you can use helium, and of course you can use hydrogen with caution. So FID is one of the most suitable detector for detecting various organic compounds, and it has a good sensitivity, you can say high sensitivity, along with a very good linear range. Okay, and that features actually make it universal detector. So let us see the advantages. Advantages is high selectivity, it is a wide linear range, it can detect almost all organic compounds, and that is why it is called as universal detector. It has fast response, it gives sharp peaks, it gives sharp peaks. Now the disadvantages, again the biggest disadvantage is that it's a destructive detector. That is, your compound which is present in the eluent or effluent, it gets consumed, it gets burned. Okay, so it gets combusted, and it requires hydrogen for making a flame. So you have to be cautious, as I have said, that you have to use hydrogen with caution, and it is non-responsive for the detection of inorganic gases as well as certain inorganic compounds. So let us move towards another detector that is called as the thermal conductivity detector. Thermal conductivity detector, actually it consists of a metallic block. You can see a metallic block, and in this metallic block it is actually composed of two cavities, and in each cavity you can see that in each cavity there are two resistors. You can see 1, 2, 3, 4. So single metallic block, two cavities, and 4 resistors are there. Okay, now what happens that when you first of all you run pure gas in all these four, you run pure gas and you measure the conductivity. Okay. Now what you do, you actually connect it with, for example, your effluent which contains the sample which has already been partitioned. So now your sample goes here, that is along with the carrier gas, and the pure gas is running here. So the conductivity of the pure gas here and here get cancelled, and the conductivity of your volatile sample gets recorded as it is connected to a Wheatstone bridge. Okay, so TCD samples senses the thermal conductivity of carrier gas, and the carrier gas sensitivity get cancelled, and what you get is the analyte which get by the on a heated filament. So a signal is observed and you actually record, your detector, that is the TCD, records that particular signal. So application is you can sense H2, N2 and CO2 also. So principle is, again, it establishes a baseline temperature. The sample molecule has a certain conductivity which is different from the carrier gas, and the carrier gas conductivity get cancelled because earlier initially you have run the carrier gas and you have actually all the four filaments, you have measured the conductivity of the all the four filaments, and when you run it again with your effluent along with carrier gas, you actually know the conductivity of the analyte alone. So filament cools because of the change in the resistance, and you actually record the electrical signal which is proportional to the analyte concentration. So this is how TCD works. So the beauty of this TCD is that it is non-destructive. Your sample does not get combust or does not mix with anything. So you get the sample. So this is the beauty, that it is non-destructive and it can detect any compound that changes its thermal conductivity, because the basic underlying principle is the thermal conductivity. So let us see the different features of it. Again, sensitivity is good but not as good as FID. The sample still, but it is still 10 to the power minus 9 gram. Linear range is again from 1000 to 10 to the power 6, a little less than FID. It is universal in the sense that it can detect both organic as well as inorganic compounds. And since it's a non-destructive, so you can couple it with FID also. Initially, your effluent can go from can be analyzed from TCD and then it can go to FID, that is the flame analysis detector. So you can use it in conformity with other detectors also. Here, the carrier gas can be helium or it can be hydrogen. Helium is preferred here because of the high sensitivity. Temperature is again not too much, it is 250 bearable temperature, not so high. So what are the advantages of TCD? Let us see the advantages and disadvantages. Of course, it is a universal detector, that it is good for detection of organic as well as inorganic compound, for certain gases also. So it is universal, it is non-destructive, that is your sample, you can recover your sample at the end, and it is simple, it is low cost, it is robust. You do not need trained people to use this TCD. But actually, if you compare it with FID, that is the flame ionization detector, then it is less sensitive. It requires pure carrier gas. Otherwise, you cannot cancel the thermal conductivity of your carrier gas in both the compartments here, because initially you have run the pure carrier gas here and here, and after that you run the vaporized solute along with the carrier gas, and that is why you have calculated the difference here and here by connecting it through the Wheatstone bridge. So here we are. So it requires pure carrier gas, otherwise in case of impurity your resolution will be compromised. So it has poor sensitivity for low concentration organics. So you have to use only for high concentration. So these are the advantages and disadvantages of TCD and FID. Okay, with this, we are going to explore the electron capture detector and other detectors in our next slides. Thank you all.